Hello. My name is Aaron McLeran. I am the lead audio programmer at Epic Games, and I am giving a tech talk today on Unreal Engine's audio engine. And we're going to sort of describe the last couple years of development and the process with which we're trying to get the new audio engine launched on Fortnite and out for new, out by default for new projects in Unreal Engine. So, if you didn't see my talk in 2017, titled "The Future of Audio in Unreal Engine," basically, I and now my audio programming team have built a new audio engine. It's basically a custom, multi-platform, full-featured audio renderer. And in my GDC 2017 talk, which you should check out on YouTube, announced some of these core features. And before I get into the last couple of years, I just kind of want to go over what that is and what it even means to write an audio engine in Unreal Engine. First and foremost, we are a multi-platform audio renderer. That means across platforms, we have feature parity. That means that a feature that works on PC should and will totally work on any other platform like Xbox One, PS4, Switch, Android, etc. This is a huge problem in the old audio engine in Unreal Engine 4 because one platform might implement one thing and not another, and one thing might work one way and differently in another. So if you're mixing your game and you're trying to make audio for your game, it's going to be difficult to make sure that it sounds the same across platforms. Because we have obviously 25 years of licensing and games being built in Unreal Engine, we wanted to make sure that anything that we do in the new audio engine is backwards compatible so that your projects will easily be able to be ported to the new audio engine. Trivially, you'll see that later in the talk where I talk in more detail on that process. But also that your knowledge of how audio works in Unreal Engine 4 will totally map over to the new audio engine. But on top of that, a big part of it is full support for DSP processing, that's digital signal processing. That means things that you might expect in your DAW for your sound design are now something that you can have in the engine in real time, like effects processing, filtering, delays, reverb, EQ, and that kind of thing. Not only do you get those effects at a submix level or a send level that you might think of in your DAW, but you also get it per source. So you can apply effects to a sound source individually, spatialize it in space, and have that a different set of effects on a different sound source. On top of that, we wanted to make sure that we allow third parties to easily integrate their tech into the new audio engine. This is something that was not well supported in the old audio engine. And by not well supported, I mean not supported at all. And so we have focused a lot on building an extensible and easy to understand audio plugin API for spatialization topics. That includes like HRTF spatialization, reverb, occlusion, and that kind of thing. We also wanted to make sure that we support real-time synthesis. As an audio engine team and sort of a vision of the future of games, we feel that synthesis is a major part of the future. Synthesis will allow games to customize their audio and their sound design tightly to gameplay and provide entirely new and exciting experiences for games. And in this slide, you see multiple screenshots from my talk in GDC 2017. It's a little bit weird, but please go check it out. On the top, I'll just describe this. It was an announcement of a synthesizer, our first synthesizer based on subtractive synthesis. This was a UI built in UMG. It's Unreal Motion Graphics, I think, and by Dan Reynolds, who was on my team at the time. Second one was a demonstration of granulation, and with a weird, floating, we called it the audio ball, just floating in this abstract landscape. It's a really cool demo. And the third image there is demonstrating sort of our spatial audio plugin API with Steam Audio. But go and check out that talk. And if this is pre-recorded, go watch that now. Then come back to this talk and you'll have some better context. But for people here watching live and in the audience, I just wanted to talk a little bit more about what this means so you can, in your mind, understand exactly what we're talking about. So this is the legacy. We're trying to use the word legacy rather than old. It's better sounding. But the legacy audio engine has multiple sort of modules here. This is sort of your standard way of thinking about a game engine. You have your project module, which is your actual game-specific code. Like if you're, say, working on Fortnite, there would be a whole bunch of code that you would write for Fortnite or any other game. Then you would have a sort of an engine module. This would be where all of your higher-level features are implemented that are shared across lots of games, like sound cues, if you're familiar with how audio works in UE4. Like sound cues would be implemented in the engine module. Then the lowest level module in the legacy audio engine is split instantly to all the different platforms. So this would be all the things that make an audio engine a renderer, like the things that actually make sound, would go to each platform. And this is just a list of example platform backends. But this is where you do your mixing, your sample rate conversion, your signal processing, your decoding, spatialization, plugins, all this stuff. So any new feature that we would write in the legacy audio engine would require us as audio programmers to do it, a dozen different times. Okay, in this case it's 6, but new platforms come online and it would just add. So it's really not sustainable. So the new way of conceptualizing the audio engine and how it helps us is you have the same sort of structure, project engine, and then before we get to the platform-specific modules, you'll see our new audio engine. So this is the layer that when we talk about the new audio engine, this is the thing that is new. So we still are adding features to the engine module layer. There's a lot of stuff, and you'll see in my talk, where we're refining and adding features and workflow improvements and stuff. So if we add that to the engine module, it'll help both the legacy and the new audio engine. But there's a lot of stuff that we're also doing that's in the audio mixer module that wouldn't necessarily help legacy implementations. And then even with the new audio engine, we still have a platform layer. Obviously, the audio engine needs to render on platforms, but that is a very thin layer. Can be as small as like 50 lines of code. It's the minimal amount of code necessary to get your rendered audio buffer to the hardware. And so standing up a new platform is very fast. It can take like an afternoon to implement a new platform for simple platforms. There still can be some complexities, like if a platform has hardware decoding, like you might see on Xbox or Switch or PlayStation, there's still some complexities that might arise that are per platform, but in general, the idea is that we've greatly simplified platform dependencies. So my talk in GDC 2017 was called The Future of Audio in the Unreal Engine, and I would like to say the future's now. This was a slide I really wanted to say for this year, but we didn't quite get there. It was very, very close, so I have to say almost. Basically, the new audio engine is not quite ready in 4.22 to be released as on by default for all platforms for new projects, primarily because we have a really high bar that we have at Epic that we're desperately, as an audio engine team, trying to achieve while balancing many of our other priorities. Basically, we need to make sure that Fortnite is using the new audio engine on all of Fortnite's platforms before we feel comfortable that it's battle-tested and ready for everybody else. That said, lots of brave licensees and games have already shipped games with the new audio engine and are shipping games now. We are using the new audio engine in anything that we do that's new projects. For example, the Chaos Physics demo that you might have seen earlier in the keynote was using the new audio engine. Robo Recall 2 years ago was the first game that shipped with the new audio engine. So it is pretty robust, but there are little issues that we're still working through that the rest of this talk is about to explain what's going on. So we have currently, as of right now, the new audio engine on for Android and PC on Fortnite. We are very close to getting it on PS4 and Xbox One. We've tested it a couple times, and it's very, very close for launching on those platforms. But after the console, we plan on focusing on iOS, Mac, and Switch. The things that we're focusing on right now on audio engine launch are performance, primarily just performance. Memory's good and everything, but it's just we're trying to get those final little bits of performance. So far, the stability is good and feature quality is good. The audio team at HQ and at Epic HQ are very happy with the new audio engine. They're excited about getting it launched on all of our platforms. It's very exciting, but very challenging. So one of the primary reasons why we want to launch Fortnite, launch the new audio engine on Fortnite, is we want to basically provide the highest level of confidence we can for licensees. Fortnite is obviously a very popular game. I think it was 250 million players that I saw on the slide earlier. I didn't even know it was that much. But basically, if you have an issue, it gets exposed. So it's a really good battle tester. If we didn't launch the new audio engine on Fortnite, we absolutely have to launch the audio engine on Fortnite, because if we didn't, we're obviously going to be stuck supporting Fortnite. And if it's on the legacy engine, it's going to be completely splitting the audio engine dev team's resources, both in terms of time and mental bandwidth and that kind of thing. So we want to be able to detach from the legacy audio engine so that we can reduce our technical debt. But it also allows us to finally move forward in some really cool initiatives that we want to do that kind of depend on us not having to support legacy backends. So there's a whole bunch of stuff that we've been trying to do for tools refactors, completely rethinking how sound cues work, how mixes work, but we don't want to shake the jello at that higher level while we're trying to swap out the renderer from underneath it. The API is really hardened. We feel really confident in it, but it's still technically in early access, just so that we have a little bit of room to change a couple of things if something comes out from our testing in Fortnite. But so far, it's gone fairly well. So since GDC 2017, what has the audio engine team done and accomplished? I just wanted to give a quick sort of overview since the last 2 years. So we've finished implementing the backends for the new audio engine on all of our platforms that Unreal Engine supports. That includes Magic Leap. I'm not going to list them all, but we have a lot of platforms in Unreal Engine. We have, as an audio engine team, also supported Fortnite launch with the legacy backend, but on all of the Fortnite's platforms. And each of these platform launches were quite challenging, especially getting Fortnite on iOS and Android and Switch. And so as a result, there's been a ton of feature work that we've done, both for the new audio engine and for the legacy. And in the last 2 years, I have grown the audio team with the help of Epic quite a bit. So we have, I'll mention now, 4 audio programmers, including myself, and we have still open headcounts. So if you're an audio programmer interested in working on an awesome audio engine team to bring the future of audio to everybody, please come and talk to me at the booth, and we'll talk. We also have a dedicated technical sound designer in the team, and an engine QA, and an audio producer. So the team has grown quite a bit since 2017. In 2017, the entire audio engine team was on stage in my talk. It was myself and Dan Reynolds, our audio QA. So, so how did Fortnite help audio engine development? I just wanted to say a little, like some of the things that Fortnite support has brought to everybody and will help licensees. So there's a sort of set of features that help both legacy backends and the new audio engine, and some stuff that was like, oh, from our testing, these are things that we added to the new audio engine. And so I wanted to talk about those as separate things. These are features that we developed that will help both the new audio engine and legacy. So we've done a ton of cook time and runtime optimizations around memory and performance. This is obviously a lot of the stuff around mobile launch. We've did a bunch of audio thread optimizations just to improve CPU performance, and a ton of higher level features around concurrency management, attenuation settings, spatialization features, and generalized workflow optimizations. We've obviously done a ton of improvements around audio streaming and decoding. Audio streaming is obviously very important for memory efficiency in a game like Fortnite. So some of the stuff that we've added to the new audio engine from our tests with launching on Fortnite are allowing the ability to customize the panning law that you use for the audio engine. We implemented stopping voices. It's a subtle feature that we noticed once we started A/B testing with Fortnite. Basically, when you stop a sound source in the new audio engine, before stopping voices, it would instantly stop, which could cause a noticeable little discontinuity at the end of the sound. So we added sort of headroom so that when you stop a sound, it takes a little bit of time to fade out, and that's customizable. We also added real-time spectrum and envelope analysis. This helped us to analyze the audio renderer while we're A/B testing. We also implemented submix recording. This was something that we could do to literally generate WAV files from a submix, compare an A/B test, and and see what's going on with the actual renderer to disk. And we also implemented null audio device rendering. This was very useful for on PC when the audio device is unavailable. We continue rendering the audio engine as if it was available until, in the future, an audio device, and by device here I mean literally hardware, becomes available to render audio, and then we flip to the hardware. It turned out null audio device rendering was also useful for rendering audio on a server where there is no audio hardware available. This is useful for unit testing, automated testing, and rendering stuff in sort of a build machine, but also pixel streaming where you might want to have a game engine running, generating graphics and audio, and have that stream to a remote location. So besides Fortnite, we've done a lot of other stuff. We have a lot of special projects at Epic. You saw Chaos this morning. That was something that we worked on. And a lot of things like that come up. And so they drive audio features as well. So one of the things that we implemented was source buses. Source buses are basically 3D submixes where rather than a submix that is generating output to go directly to the hardware, even if it's in a graph, a source bus is itself another sound source. So you can basically send sound sources to another source, which is a mix of multiple sources, and then move that around and apply source effects and do things with the sound source as if it was just the sound source. We also implemented a couple other synthesis methods, source and submix DSP effects. I'm not going to list all of them, but there's a whole bunch of new stuff that we did in the last couple of years. We also had a couple months to focus on rethinking sort of the initial first pass on the plugin API. So we kind of refactored a little bit of that, and it is way more robust and is basically implementing all of the features that we're aware of in spatial plugin APIs. We also implemented a bunch of MIDI improvements. And we have done some work to clean up the native VoIP voice over IP that we had in the engine. This is different than the online services announcement that was in an earlier talk. We are also working on that, but this is different than that. So what I want to talk about next is a couple of interesting case studies, just problems we ran into while testing the new audio engine on Fortnite. I thought would be interesting to go into detail just a little bit to give you an idea of the kinds of problems that as an audio engine team we wanted to solve. So the first one, for example, is how we A/B test Fortnite with the new audio engine and without the audio engine. In the beginning, we found that the workflow of changing an INI file and relaunching the game was very slow to see if some volume thing was fixed or some sample rate conversion issue was fixed. So we were doing a lot of video capturing and A/B testing and video capture, but that is not great. So we tried a number of other things. We had a console variable or a command line that allowed us to quickly swap, but still required a restart. So we came up with a method to swap the audio renderer while the game is running using a CVAR. This is basically just au.is using audio mixer, and you say 0 to make sure that it's not using 1, and 1 to make sure it's using it. So while the game is running, we can actually quickly say, what does it sound like without the audio engine, the new audio engine? What does it sound like with a legacy audio engine? Not only that, but we can use this as a tool to publish hotfixes to the client remotely. So we can actually test Fortnite with the new audio engine live. Like a player can be playing the game in the legacy audio engine, go back, queue up, and play again with the new audio engine. And we can just then look at live metrics and see what's going on. But it's also very useful for the sound designers to test their sound design and point out issues that they discovered with the new audio renderer. So that was, I would say that was a case study of like how we toggled back and forth. The second case study is analyzing loudness. Loudness is probably one of the most challenging aspects of a game engine for audio. There's a lot of things that factor into it, many gain stages. You have spatialization, attenuation, dynamic mixing, many, many things that factor into loudness. So while we were testing, we noticed that only certain sounds in Fortnite seemed to be a little bit too loud than other sounds. And isolating what those sounds were, we discovered it was 3D sounds specifically. We measured the loudness. It was precisely 3 decibels too loud. We also where originally, before we measured it, we actually were made a lot of assumptions that it was probably a missing gain stage or something I had missed in the new audio renderer to translate from the legacy to the new audio engine, or some weird thing that might have been going on with the legacy audio engine that isn't happening in the renderer in the new audio engine. But essentially, what we tracked it down to was a difference in panning law. So panning is the method of doing traditional spatialization in a game. So I say traditional to distinguish it from an HRTF, like binaural render. So panning is basically an automated process of like doing left and right pan in your DAW. So if the sound source is located over here, it'll figure out the geometry of which speakers it should be between, and then it'll come up with a volume blend between different speaker channels. So as an audio programmer, I strongly believe that equal power panning is the preferred method of panning. And when I first wrote the audio renderer, I just did that as the way to pan. And then I forgot that's how I did it. And so later when we were testing with Fortnite, I just wasn't thinking of that as something in the gain stage. And basically, that was the problem. And so we, as a result, added panning law as an option. And then for Fortnite, we just default to linear. So and the TLDR of that is Fortnite is linear panning, and the new audio engine was by default equal power panning. And I just want to go into a little bit of detail about what that means for people who aren't audio programmers. So on the left here is linear panning, and the right here is equal power panning. Linear is like what you'd expect. This would be like, for an example of a stereo mix. It would be the same sort of thing with the surround sound. You would call that pairwise panning, as you figure out the geometry between like a 7.1 mix. You'd say like, oh, it's between this channel and this channel. It's blended between these two for a thing to the, rendering to the left. And you would just linearly pan between that. So that's what would be on the left here. Essentially, you just want to hold constant the amplitude of the speakers as you pan across. So on the right here is, instead of holding the amplitude of the speakers across, you hold the power of the speakers constant. And it produces slightly different curves as you pan. There's multiple equal power laws that you might articulate. Basically, as long as it satisfied the thing on the left squared plus the thing on the right squared is equal to 1, that would be equal power. My favorite sounding one is cosine. This is called cosine law. And essentially, it just uses your traditional trigonometry identity, sine squared plus cosine squared equals 1. The problem here, as you might guess, is that there's a little bit of volume here difference. So for a 3D sound pan to the center, it's fundamentally going to be 3 dB louder than linear panning. So if you're doing equal power panning, you'll get a little bit of a volume boost. And that's exactly what we measured. Flipping it to linear fixed the issue. So why use equal power panning? Volume perception is nonlinear. What that means is, essentially, I used to teach high school physics. The sort of pat answer is, to hear something twice as loud, for you to perceive it as sounding twice as loud, will require 10x the amplitude. And that is a very confusing thing for everybody to think about. We're very linear beings as humans. And so it's hard to conceptualize what that means. But essentially, if you want something to sound the same volume, you need to think about power. Power is the fundamental thing that we're hearing when we're thinking of loudness. I recommend using equal power if you're starting a new game. If you're trying to do a port to an old game that was using linear, keep using linear. So otherwise, you'll force all of your sound designers to remix the game, which we didn't want to do. All right, so third case study is memory and performance. This is a little bit less exciting. I don't know if I think panning laws are really exciting. I don't know about you guys, but anyways, so for Fortnite, we have a really high bar for memory, obviously, and performance. So there's a number of tools that UE4 has. I'm not going to go into extreme detail of what all those tools are, but we essentially are using our own tools for doing low-level memory analysis. That's LLM. It's a tool that is available in UE4. You can mark up your code according to different scopes and analyze different behaviors in terms of memory allocations throughout your code. We also have tools for analyzing performance. This tool, that's called CSV tool, is something that we use. We also have nightly bot soaks that just crunch through, running tons and tons of bots. We also have a replay system in Fortnite, which is useful for players to look at their game, but also useful for engineers to look at performance. So you can run a game with deterministic output and sort of compare A and B with various changes. And we also have a lot of analysis from live ops that we can look at. So I just want to show you a little bit of some graphs. This is something I pulled up from, I think it was maybe 4 or 5 months ago when we were testing for PC. I just had some beautiful graphs that kind of show it nicely. So basically, the blue line is the new audio engine, and the light blue line is the legacy audio engine. And this particular graph is just game thread time. So you can kind of see it's mostly matching. Sometimes the new audio engine is a little bit worse. Sometimes it's a little bit better. So it's pretty much on parity. So the impact on, this is a graph that measures the impact of the render thread. It's a similar story. There shouldn't be any direct interaction of an audio engine with a render thread. So this is probably describing async decoders and tasks interacting, but mostly should be similar. And this is the sort of worst case scenario of both. So you can see both the game thread and the render thread sort of added together in worst case. Just sort of the worst timings of both added together. And you'll get the frame time. You can see it's very, very, very close with the new audio renderer versus the old. And this is on PC. So this is comparing X-Audio 2's implementation in UE4 versus our audio engine. And then finally, this isn't finally, but this is moving over to memory analysis. This is using the LLM, low-level memory analyzer. So you can show sort of the memory usage over time through a replay. And you'll see here that the dark blue, which is the new audio engine, is always just a little bit less than the light blue. So we actually use less memory than the legacy X-Audio 2 consistently. This is just the similar kind of graph, but doing a direct call to looking at physical memory allocated. And you'll see, again, generally, the new audio engine is well behaved for the majority of the time. It kind of matches at the end. This kind of gives you an idea of what we're staring at, trying to figure out what's going on. And then this is a virtual memory allocated in the same run. All of these are in the same run, just generating different data outputs. And you'll see the virtual memory used is identical. So the final case study I want to look at is SIMD optimizations. So if you're not an audio programmer or a programmer in general, it's probably boring, but SIMD stands for single instruction, multiple data. So basically a low-level platform-dependent intrinsic that allows you to do 4 things, 4 mathematical operations when normally you would have to do that 4 different times. It basically, from the CPU, is as if it was 1. So you can get basically a 4x speed up. In best case scenario, it's not necessarily 4x. There's overhead that can happen in setting code up for it, et cetera. But it's a really good thing to try to look at how to refactor your code to use this tool. One of the speed ups that can happen is also just organizing your code to use it to reduce cache misses. So in a CPU, when you're trying to do an operation at the low-level register, you have to load data. So the cache is sort of the fastest memory. And if you don't have your data in the cache, it'll have to go back to your RAM, your main memory. And that can be very slow. That's called a cache miss, if you didn't know. And so it's good to have all your data where you need it to do your math so that it's basically as fast as it can be. And SIMD just happens to be a thing that kind of requires your data be organized to optimize for cache coherency. So you get speed ups in multiple ways if you go and try to organize your code to work with SIMD. So one example, we've done this all over the place in the audio engine, and we are doing it in more places. But this is an example of a problem that we applied it to and saw massive improvements. And I just wanted to talk about it a little bit. So I'll try to do this a little bit quickly. But basically, the problem is you have a source file trying to map to an output channel. So essentially, this is the panning at the lowest level. You have a sound in a location, and it needs to map to 5.1 or 7.1 output. And so the problem kind of becomes expensive if you have like a 2-channel file mapping to an 8-channel output. It could be 16 sort of operations all overlapping. And the naive but clean-looking implementation is very bad. So this was a prime candidate. We also discovered this as primarily the most important or most expensive part of the audio render. So we're like, let's make this faster. So this is the code. I'm not going to go into detail, but for programmers out there, you can screenshot it and like look at it and go, that's so clean looking, but holy crap, is that expensive. So this is, you can see 3 for loops embedded on nested with each other. It's jumping through buffers. It's extremely cache incoherent. But it's only 34 lines to do a complicated operation. So instead of that, we broke it up into a heck of a lot more lines of code. Instead of looping through things, we just upfront figure out what function to call given the conditions. This is very snipped. It's a lot bigger than this. You can see that instead of a loop, it just unwraps that and just calls a function. So for example, if your input channels are 1 and your output channels are 8, you would just call mix mono to 8 channels fast. And that function looks like this. It's very ugly. Essentially, you have an input buffer, a destination buffer, the number of frames you want to render, and then your starting speaker map and your ending speaker map. And this function essentially loads everything up into these vector registers, which are required for SIMD operations. And not only does the operation to map like a mono file to an 8.1 or 7.1 output, it also is doing the interpolation through the frame. So by combining those two operations, making the code cache coherent, we saw 30x speed up, literally 30x speed up. But this is in worst case scenarios. We built maps to slam this particular aspect of the engine and basically did sort of randomized performance capture, like random sampling performance capture. We saw a 30x speed up. The code is a lot more confusing to look at, but it's a lot faster, and it's awesome. So we are in the process of SIMDing a lot of aspects of the audio engine. We've done that for a lot of areas. Some of the areas that we still have yet to do are reverb, effect, EQ, other effects, and things like that. But there's a lot of more work to do to get this kind of speed up elsewhere. So I wanted to talk about some new 422 features briefly. So we've done an overhaul of the MIDI plugin. So we had a MIDI plugin before 422, but now it is easier to use for MIDI input. But we also have MIDI output, and it's been a lot of fun. So come to the expo, our audio booth at the expo, to play with some cool stuff. We are launching a prototype of a new direction that I have an idea for, interactive music. The time synth, which I'll talk about in detail here, is the fundamental code required, or the fundamental feature required for doing sample-accurate clip sequencing. We also implemented a new approach for concurrency. So concurrency is the feature that allows you to control how many sounds play in a particular group. We've added the ability to layer them, so you can have more complicated logic to manage what sounds play in what groups. We also improved the workflow on asset importing. It's been one of the pain points that some of our licensees have talked about improving, so you can import a number of asset types. And we've implemented a baked-in real-time spectral analysis. This picture here is where we implemented that in Fortnite. You can see in creative mode, you can get sort of real-time analysis to drive visuals of toys and stuff like that. We've also used that feature on a skin in Fortnite, where all of the emote music has baked analysis that drives Marshmallow's skin. And so look for more ridiculous shaders driven by baked analysis. It's a really cool feature because you can get sort of shader-driven stuff without having to do the CPU expense of doing analysis. So we have a couple demos that were shown at GDC I also wanted to talk about. I already talked about the time synth, so I'll go into a little bit more detail here. We have a demo that we put together. It essentially is inspired by the quantization clip queuing system that you might see in Ableton Live, where you have an audio clip defined and you want to trigger it on a particular quantization boundary. It's pretty much the only way to solve this problem if you want to do interactive music from blueprints, because Blueprint runs on the game thread, and the timing of the game thread is not going to be precise enough to do like audio sequencing. And so what you want to do is have a clock on the audio renderer that is at a very precise rate with quantization events lined up. And you can say, hey, I want to play this clip on the next bar, or I want to play this clip on the next 4 bars, or on the next 16th note, or I want this clip to play on the next 8th note, etc. And so this is essentially a synthesizer that decodes audio clips and renders them precisely at exact quantization boundaries. So you see the screenshot on the right here is a definition of a time synth clip. So you can see the audio file is at the top here. You can see that it's just a pad, a sound wave. It supports multiple sound waves with randomization, so when you queue up a clip, it could randomly pick different clips. It also has a feature for volume control. This is because you might want to have multiple clips organized in groups and then control them as a group differently than another group. And that would be the second category here, is just sort of how the clips, like volume controls, is done. And then we have the time control. This defines the clip duration, the clip quantization. So when you play that clip, it knows when that clip needs to play in terms of the quantization event boundary. And this is a snapshot of what the API might look like. Play a clip on a time synth component. So this is a demo showing this, with put together by Rob Gay on our audio team. Here's a second little demo here. So you saw in that video 2 different sort of examples of potentially using the time synth. Rob was learning Blueprint while he did this, so it's pretty awesome. Rob started with this in November on the Audio Engine team. So this is something we have set up in the booth at Expo, down at the Epic booth, so come and check it out. So the other thing that we are talking about this year at GDC is a new synthesizer. This synthesizer is based on wavetable synthesis. It was implemented actually by an intern that started with us just about a month and a half ago, 2 months ago, Max Hayes, who's in the audience. So when he showed up, I was like, we don't have time to do a lot of stuff with you. Just do something fun and cool for GDC, and it's awesome. We'll talk about it. And it's really awesome. Basically, we use the UE4 curves, which are this on the left here is just a screenshot of a UE4 curve. And essentially, it snapshots the curve into an audio buffer that you can then synthesize. It becomes one cycle of an audio buffer, and it can sound really cool. So rather than just doing that, Max went ahead and built a bank of them and then allows you to blend between them. And we decided to hook it up to this MIDI controller, fader port, to show off the new MIDI input-output feature. And so the fader port here visualizes the curves in UE4 directly, so you'll see that the fader ports move according to the curve, and simultaneously the fader port allows you to author the curves. And it's a really cool demo that allows you to sound design some really neat sounds, and Max put together this next video. So he has a MIDI controller here that he's using to play the notes. He's cycling through the different buffers on the right here that you see with the different curves. And now he can continuously interpolate between them smoothly. You see it's all a live connection. So he can author the curves in UE4 and see it react live on the fader port. And of course, as he controls it on the fader port, it's also talking to the curve in UE4. You can hear the effect on the wavetable synthesis in real time. You can see the blueprint in the background is executing, just to show you that it's live. So you can cycle between the different tables and then interpolate between them. It's very fun. You can come down to the GDC booth and play it with it yourself. We also have a filter that he's controlling that allows you to sort of use it as a subtractive synth that subtracts out the tones. Oh, he also went one step further and added an LFO. So it'll oscillate off of the index you've set. Of course, it has an ADSR. There's no anti-aliasing on that, so it's aliasing like crazy, but that's fine. It sounds great. We're really excited. Please come down to the booth to play it. Final thing we wanted to talk about as a GDC thing is chaos audio. So if you haven't seen the chaos destruction demo, you can go and play it down in the Epic booth. You should also check it out online during the keynote. The chaos destruction demo features the new audio engine. We decided to use that. Dan Reynolds was the sound designer on a lot of it and built a whole sort of destruction audio management and blueprint. We do have the editor project of this, so you can come and check it out and get Dan to show you some of the techniques he used. But we're very proud of how the audio engine worked in this demo, and it's one of the things that we wanted to highlight during GDC. So where do we go in the future with the audio engine? It's a hard question. These are sort of things that are currently on our minds about where we want to take things. Some of these are actually in development at various stages. But one of the big things we want to look into is what we've decided to call stream caching, or conceptually you can think of it as audio load on demand. This is kind of the key feature that we need for large open worlds or very dynamic games, where you don't necessarily know what audio you need to play at what time. So this feature will allow us to basically have audio load when it's needed and unload when it's not needed in a way that's independent of the general referencing mechanism in UE4. It's sort of the generalization of the concept of audio streaming, which is why we're calling it stream caching. Another thing that we want to improve on in UE4 is volume mixing, basically volume parameter modulation. Right now, UE4 uses sound classes and sound mixes to drive and define game mixes. We feel like we can do a simpler and better and more direct job with a different system. So this is a work that's in progress. And I think it'll revolutionize how people think about mixing in games. Another thing that we have found is something we need to implement is sort of DSP analysis and profiling. As the new audio engine brings all of these features around digital signal processing, we want to be able to understand that, what's going on, performance, even understand the spectral characteristics of what's going on with your mix, and build that tool directly in the submix graph tool directly. And then finally, we kind of want to rethink what it means to do audio scripting. Blueprint is obviously a very powerful tool, and we spend a lot of time getting people excited about blueprints for audio. But blueprints have a fundamental flaw with respect to audio, and it's on the game thread. So we are trying to think about ways to bring the power of blueprints for audio in a more direct fashion. That could mean having a blueprint VM running in the audio thread, or something else entirely. So this is sort of early R&D things that we're thinking about. If you are familiar with audio domain-specific programming languages, there is a lot of really cool stuff out there, and it could be something that we bring to UE4. So that's kind of So that is my talk. Any questions? Thank you for coming.